Hey YouTube, so last time we made the simplest 3D that I could think of, which is just one dot in 3D space that is rotating around. And this time let's expand on that a little bit. So the first thing I'm going to do is I'm going to take these two lines here that we use to actually draw the point and put that in its own function. So I'm just going to take that, cut it out, and then go over here, and I'm going to make a function that's gonna return the distance to the point. Actually, no, it's not returning the distance to the point, it's returning the actual point itself. So I'm gonna call it draw point. And it's gonna take as an input a vector3 ray origin, a vector3 ray direction, and a vector3 p, which is the 3D location of the point. And I'm gonna stick that in there, and over here I'm just going to return that value d. Return d. And so now let's go over here and see if our function works. I'm going to float d equals draw point, and then I'm going to stick in my ray origin, my ray direction, and my p. And so this shouldn't change anything. So let's see. All right, so that compiled, nothing changed, so that's all great. Now the next thing I'm going to do is, I'm going to make my point a little bit smaller, because I'm going to draw more points. So let's see here, 0.05 and 0.06 should be good. So you see that it made the point a little bit smaller. And now I am going to draw a cube. So we're going to get rid of this rotating point, and we're going to replace it by something else. So let me get rid of this, and I'm going to just initialize my float d as 0. And now what I'm going to do is I can add more and more points just by adding to that value d. So let me just stop this here for a second. So now over here I'm going to put the corners of a cube, and a cube has eight corners. So let me just copy something 8 times first to start with. So we have that. All right, so that would be 1 point, and I'm going to copy that 8 times. Hang on a second. So that's 2, 4, 6, and 8. Okay, and now I'm going to have to put all the corners of the cube in here. So the corners, like in this case, is just all the different combinations of 0 and 1 for 3 different numbers, and that's just counting in binary from 0 to 7. So the first one is 0, 0, 0, then I have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, and last but not least, 1, 1, 1. All right, so let's see what that does. And as you can see, that drew a few points. And these are all the corners of the cube. It's just that some of them we can't see because the camera is too close. So let me just press play again here, by the way. So let's move the camera back a little bit. So to move the camera back, we have to move the ray origin back, first of all. But if I just move the ray origin back, and I don't move the screen back, then essentially what I'm doing is I'm zooming in instead of moving the camera back. So if I just go really quickly over here, so if this is my ray origin and this is my screen, again, if this is my ray origin and this is my screen, so now I just see from here to here. If I just move my ray origin back and I don't move my screen back, then I'm doing this essentially, which is zooming in. as opposed to moving the camera back. What I need to do is I need to move my ray origin back, and I need to move my screen back in order to keep the same angle. I hope that makes sense. So let's move back here. So just moving this back here is not good. So if I do that, it will just zoom in at the same time. So you will still not see what you want to see. So we have to also move back the screen itself. Not point to point. All right, so now I move the screen back and I move the ray origin back, and so now I can see the entire cube. And you can see that this is a little bit cumbersome to move the camera around like this. And this is just moving it. Rotating it would be a total headache to do like this. So what we really want is something else. So let me go back here. Let's go down. So what we really want is we want something where we have a ray origin, and we have another point in 3D space that is called the lookat point. I'll call it LP. And every time the camera system will automatically adjust the screen based on where the ray origin is and where the lookat point is. So if I move the ray origin to somewhere else and I keep the lookat point the same, then now I will look like this, and I will have my virtual screen like that. And I'll have my rays coming like this, right? My ray directions. And over here, it's the same thing. So now my screen is over here and my rays go like this. So this is basically what we want. We want a system where we have just 2 points, a ray origin and a lookat point. And based on that, we can adjust the camera in any which way we want and frame a subject or whatnot. So let's go down here and let's revisit for 1 second what the ray direction was. So the ray direction, if you remember, if I draw the screen kind of in perspective, that's the center of the screen, and this is my ray origin over here. Ray origin. So the ray direction was defined by the intersection point of the screen. So let's say we're intersecting over here, and we call it point I, and having the vector that goes from the ray origin to that intersection point, right? So the ray direction was the intersection point minus the ray origin. Okay, so now let's just recap what the intersection point was. So if I take the screen and I move, or I look at it straight on, and again, here's the center of my screen, let's call it C, then, and this is my intersection point over here, let's call it I. Then my intersection point was just, well, we start at the origin and we go uv dot x steps to the right, and then we go uv dot y steps up, right? So let me write that. So the point I was, we start at the origin at the center of the screen, which is point C, plus, and from there on we're going to move uv dot x steps to the right, plus uv dot y steps up. Okay, and you might say, well, we've never talked about right and up, but that's not really true, because let me just go over here. Right, let's just call it R. If in the case of the previous video, like our screen was just straight, meaning that our right direction just coincided with the x direction, and the x direction is in vector form 1, 0, 0. And the same thing as the up direction, let's call it u, is the same thing as the y direction, which is 0, 1, 0. Right? And for completeness, the forward direction, so into the screen or out of the screen, let's call it f. That's the same thing as the z direction, which is 0, 0, 1. So this is in the case of a screen that isn't rotated at all, that is just completely aligned with the world. So in order to calculate this ray direction over here, all we need is these three vectors. If we figure out what these three vectors are, then we can calculate the ray direction for an arbitrarily rotated camera. So let's try to figure out what these three vectors are. So now the first one, the easiest one to calculate here is the forward vector, because the forward vector is just, if we take the ray origin over here, and we take a lookout point over here, so the forward direction is from the ray origin to the lookout point. And so the forward equals the lookout point minus the ray origin. So that one's simple. Now for the other ones, we have to do something else. So let me just draw here like a normal, the normal three axes that you have in the world, right? So there's the x-axis, and then there's the z-axis, like over here, and they have a 90-degree angle between them. If we want to get a third vector that is perpendicular to these two vectors, we can use the cross product again. So you might remember this from high school. The cross product between two vectors is a third vector that is perpendicular to those two vectors. And if you don't know about this, there's plenty of YouTube videos that you can check out. So if I take the cross product between these two, then I get a third vector that is perpendicular to both these vectors. So this vector and this vector are 90 degrees. This vector and this vector are 90 degrees. And this vector and this vector are 90 degrees. So if we take that and if we just imagine that our forward vector here, so our forward vector, let's just say our forward vector is over here, and our forward vector lies in the same plane as the it lies in the xy plane. So if I now take the cross product between my forward vector and my up vector, which is this one, right, the y, then I will get this vector. Let me change the color. I will get this vector here, because the cross product between them is 90 degrees perpendicular to both of them, which is this one. So my right vector is just, a cross product between the world up vector, which is y, so the world up vector y, and the cross product, so I'll do a little x, don't confuse it with x, and my forward vector. So the cross product between the world up and the forward vector is my right vector. And now we only have to do the last vector, which is the camera up vector, right? So the camera up vector would be in this direction, camera up vector. Well, the camera up vector, we can just do the same thing again as what we did before here, which is take the cross product between the forward vector and the right vector that we just calculated. So the up vector is just a cross product between the forward vector and the right vector. And now we have all the three vectors that we need to use this formula to get our intersection point, right? To get our intersection point over there. And when we have our intersection point, we can use that to calculate our ray direction. So let's do that. So let's go back here. Put my pen away. All right. So let's see, what do we have here? So the first thing that we want to do here is define a lookout point. So vec3 look at equals vec3. And let's just make the lookout point exactly the center of the cube. So the cube goes from 0, 0, 0, 0 to 1, 1, 1. So the center of the cube is 0.5, right? So that's our lookout point. the next thing that we want to do is we want to start calculating our 3 basis vectors. So first is our forward vector. So our forward vector is the look at position minus our ray origin. And there's one thing that I didn't mention before, is that these basis vectors, we want them all of the same length. We want them all of unit length, meaning of length of length 1. So what we have to do here, because the lookup point might be arbitrarily far away from the ray origin, we have to normalize this. So normalize, and so what normalize does is it just makes the vector of unit length, of length of 1. So that's our forward. So now we go and make our right vector. So our right vector is just a cross product between the world up vector. So that's vec3, the world up vector, which is vec3, which is the y, right? So it's 0, 1, 0. And the forward vector we just created, so f. And now our last vector, the camera up vector, vec3 u equals, it's the cross product between the forward vector and the right vector, so forward and right. So now that we have our 3 basis vectors, and the other ones I don't have to normalize them because because over here I normalize the forward vector, and then over here I'm taking the cross product between 2 vectors that are already of length 1. So that vector is going to be of length 1 as well. So we don't need to normalize here. So now that we have the 3 basis vectors, we can calculate our intersection point. So vec3i, and actually before I do that, we have to calculate the center of the screen, right? So let me go back here. So what is the center of the screen over here, this thing, the center of the screen? Well, the center of the screen, it's the same thing as over here, right? Center of the screen. So the center of the screen is nothing more than the ray origin, like the vector from, it's the ray origin plus the forward direction. So the center of the screen, C, equals the ray origin plus the forward vector times the distance between the ray origin and the screen, which is our zoom factor, zoom times zoom. If you remember, if we go back over here, it's this distance, right? So if our zoom is larger, then we pull the point back and we have like more, we have more zoom. So let's go back here. So let's put in vec3, the center of the screen equals our ray origin plus the forward vector times the zoom. And the zoom, we're going to make that just as a floating point value. And so float zoom equals, just make it 1 for now, or we can play with it later and see what it does. So now we can calculate the intersection point of the screen, which is the center of the screen plus uv.x times the right vector plus uv.y times the up vector. All right, and now we're almost there because now we can calculate our ray direction. So our ray direction is just our intersection point minus our ray origin. All right, so cross our fingers, try to compile it, see what happens. All right, so I can see that the lookup point worked and everything seems to be okay. So now let's see what we can do with this fancy new system here. So first of all, let's try to zoom this. So if I press 2, I imagine that I would zoom into the cube. And that's exactly what it does. Great. So now let's move the camera up. So I can go over here, put it at 4. And you see that it moved up. It's like maybe it moved up a bit much, it's harder to see, but it moved up, but it still keeps looking at the cube. So that's great. So let's take this here, move it all the way to the top, and let's end with the camera rotating around the cube or orbiting around the cube. So just go here, and then I'm going to say over here for my X position, I'm going to do 3 times the sine of t. And here I'm going to do -3 times the cosine of t. And let's see what that does. And now I have a rotating camera. And you can see that it zooms in a little bit here at certain points, and that is because my cube, like when I made the cube was not in the center. Okay, the cube has one of its corners at the origin, but the cube itself, so the center of the cube is not at the origin. And right now what I'm doing is I'm orbiting around the origin here. So that's why sometimes I come closer to the cube and sometimes I go farther away. But I'll leave it to you to figure out how to make that so it doesn't zoom in and zoom out. So you'd have to move the cube, either move the cube or move the circle that we're orbiting around. So anyways, I hope you see that this is a lot more powerful than what we had before. And it's a great base to start building something cool on. So I hope you like it, and I'll see you next time.